Have you ever wondered what makes a software architecture good and stand the test of time? How can we avoid systems getting crippled by complexity and becoming impossible to build on? Join me for a deep dive into the foundations of software complexity and the visualization of technical debt. Learn how to design and build software without the expensive rewrites. My name is Derick Chen, and this is BuildWithDC. First, for us to design and build good software systems, we must understand what good looks like. And to do that, we need to have a first principle understanding of the challenges we are dealing with. Only then, we can establish the long-term goals of software architecture and measure the relative effectiveness. Now, as we all know, the purpose of the software system is to facilitate business transactions and deliver value to the end users. But as the underlying business succeeds and the product reaches a product market fit, the software system needs to address these changes in order to continue serving users effectively. There are four primary contextual changes that we all need to address in the lifecycle of a software. Number one, changing product requirements. When the product needs to be evolved or refined for a better product market fit, these new needs can expand or shift the product scopes. Number two, changing usage level. When the number of concurrent users or the data generated exceeds the optimal handling capacity of the existing solution, or perhaps certain traffic patterns emerge that give us opportunities to further optimize. And number three, changing technology. This refers to the emergence of newer and better solutions for the existing challenges. Additionally, when new dependency vulnerabilities, deprecations, and end of the support are announced, we must react quickly. Number four, changing integrations. This applies both in the software we're building and the team. There may be more modules, external systems, and tools that need to be integrated with. Or you may have new developers on board or collaborations with other teams. These constant contextual changes pose a severe challenge to the software systems in either the behavior or the performance requirements. Quick caveat. I use the term behavior and performance requirements instead of functional and non-functional requirements that you may be familiar with. In my opinion, non-functional requirements is a particularly poorly worded concept, but an important one that somehow falsely signals a lower priority than its functional counterpart. It is also not quite self-descriptive. So instead, I'm using a more ubiquitous and self-explanatory language here: behavior and performance. Behavior is what a software does, and performance is how well it does it. The idea that software can be built once and so many times absolutely ignores this constant and universal challenge. You can't keep selling software you built when it's no longer relevant. So we need our software systems to be malleable enough to adapt to these constant changes. An adaptive software architecture gives the company or organization the evergreen competitive edge of a high rate of innovation. Therefore, after addressing the existing behavior and performance requirements, the gold standard for evaluating how good a software architecture is how responsive the architecture is to adapt to new and additional requirements. Or simply put, the adaptiveness of the software. The convenient and less ideal way to tackle these new requirements is usually a conservative approach. Keep what we have right now and build the features on top of that. Don't fix it if it's not broken. But eventually, this approach will create systematic and structural rigidity that slows down the iteration speed. This is a symptom of lacking adaptiveness at a software system level. Not gonna lie, it's tempting to address one engineering challenge at a time and fix this with more tools, frameworks, and practices. There are plenty of software technology offerings and agreed upon best practices that are not fully contextualized. This approach results in a swamp of different integrations that makes the process of building software ever more complicated. It's still fine for the time being if you have a capable team that can manage this software system, but when this crosses a complexity threshold that your team can comfortably iterate with, the complexity becomes deeply rooted and is difficult to remove, creating a vicious cycle. Yet not all complexity is bad. As the underlying business processes become more nuanced and varied, complexity does get transferred into the technical solution. But that is not technical debt. Technical debt is the result of software artifact complexities that are left unoptimized. We can mentally visualize the complexity in a software system by reviewing the cyclomatic complexity of the software artifacts. Any software system can be represented by a multi-layered graph structure. Each layer usually shares the same fundamental building blocks. For example, a programming language, a protocol, or framework. The application code is one layer, and infrastructure as code is another layer. Within each layer, we can then represent processes in nodes and edges, like in a graph. A node represents a logic processing unit, and an edge illustrates the integration and dependencies with other nodes. For example, in a simple Python script with functions, the nodes are the functions and edges are the function calls and invocations. In a distributed system, the nodes are the independent software modules that may be deployed to multiple hardware, and the edges are the integration interfaces such as asynchronous events or REST API calls. Now, going back to the topic of complexity. Complexity is essentially the combined order and size of this graph. Order refers to the total number of nodes, and size is the total number of edges. Naturally, as business processes become more complicated, complexity in the software increases as well, as we need to model new processes and more branches of logic. But this does not necessarily mean that you have added to the technical debt. Technical debt is the unoptimized complexity, the redundant nodes and edges that we could potentially remove while still meeting all the requirements for the software. And this is the goal of refactoring. Some people argue that by distributing your software system, you are shifting complexities around. That's absolutely true. And I will even say that additional complexity needs to be introduced in order for everything to work together. So why do we do this? We have to remember that the goal is not simply to reduce the total net complexity in the software system, but deliver software at a high speed of iteration. Sometimes this is achieved by reclustering the complexity and matching the skills level and the complexity tolerance of the team that is assigned to own this particular piece of software unit. By going distributed, we're facilitating effective small team collaboration and iterating faster in parallel. But refactoring is expensive. It takes 10 times more effort to remove and rewrite something in production than to prevent it in the first place. We run a risk of unexpected side effects or accidental production issues that can severely derail the refactoring effort. So, in our build phase, we should minimize the accumulation of complexity and streamline processes and design before implementation. This will result in a positive multiplier effect in future iterations too. as your software project is more nimble and has greater adaptability in addressing the 4 constant contextual changes that we have discussed earlier. That is why adaptiveness is so important in software, and it is a key measurement of robustness. In summary, adaptiveness in software is the responsiveness to new changes and meeting fresh requirements. And we approximate this responsiveness in time and effort. In the next part, we will discuss how we will achieve adaptiveness for any software systems that you are building. As a sneak preview, we need to solve a 3-part problem according to your unique context and find a point of balance between your business, software, and team. Only when we find an adaptive state of equilibrium, we will be able to innovate fast at scale. If you want to learn more about how to practically design and build adaptive software systems, remember to like, comment, and subscribe to this channel as we dive deeper into the tactical approaches in the upcoming videos in this series. My name is Derick Chen, and I will see you in the next video.